Have you ever looked at a modern building? One of those twisting, flowing, unbelievable structures, and just thought to yourself, how on earth did they even build that? I mean, take a look at this. This is the Morpheus Hotel in Macau, designed by the legendary Zaha Hadid architects. It's less of a building and more of a sculpture, wrapped in this insane freeform steel skeleton. Seriously, how do you even start to design something like this, let alone build it with perfect precision? You can't just sketch this out on a napkin.
And it's not a one-off thing. These kinds of impossible shapes are popping up everywhere. You've got the Haidar Aliyev Center, which looks like it just melts right out of the ground, or the Metropole Parasol in Spain, this gigantic wooden waffle structure. They completely defy the straight lines and square corners we're so used to seeing.
So what's the connection here? You might think it's just some crazy new futuristic style, but that's not quite it. The real secret, the key that unlocks all of these incredible designs, isn't what they look like, it's how they're made. The revolution isn't in the style, it's in the process itself.
Okay, so we're talking about a fundamental shift in thinking. Architects are moving away from designing static objects, drawing one wall, then one window, one piece at a time. Instead, they're designing dynamic systems. They're not just drawing the building anymore. They're writing the set of rules that can actually generate the building.
Here's a great way to think about it. Traditional design is like baking one cake. You follow the steps, and you get that one cake. Parametric design, that's like writing the recipe for the cake. Once you have that core recipe, you can change the ingredients, the parameters, a little more sugar, a different kind of flour, and you can create an endless variety of perfect cakes.
So officially, what is it? Parametric design is all about using computer algorithms to define the relationships between parts of a design. It's not about telling the computer to put a window at specific coordinates. It's about telling it, hey, the window's height should always be half the wall's height. So if you change the wall, boom, the window automatically updates. Everything is connected. And this is the game changer right here. The old way, the non-parametric way, is completely manual. If you decide to change a wall, you've got to go back and manually redraw the roof, the floor, everything connected to it. It's slow, it's static. With parametric design though, everything is linked by those rules. The entire system is dynamic, it adapts. So how does this whole engine actually run? How do you get from a simple set of rules to one of these mind-bending buildings? Well, it really all boils down to three core components working together. First, you've got your parameters. These are your basic ingredients, things like the building's height, the materials you're using, or the angle of a curve. Then you have the algorithms. This is your recipe. It's the logic that connects all those ingredients. And finally, and this is the really powerful part, you have feedback loops. You can run simulations to test the design. Is it energy efficient? Can it withstand high winds? That data then feeds back into the model, letting you tweak and optimize the result. Now, this idea didn't just pop up overnight. It's been evolving for a long time. The seeds were planted way back in the 60s with early computer-aided design. By the 90s, pioneers like Frank Gehry were using super advanced software for projects like the Guggenheim Bilbao. But the real game changer came in the 2000s, when tools like Grasshopper made this powerful process accessible to pretty much every architect out there. So yeah, these complex shapes look absolutely stunning. But why does this method really matter? Because the true power of parametric design isn't just about making cool shapes. It's about creating buildings that are smarter, more efficient, and just better. This is where it gets really practical. You can optimize a design based on real-world performance, using environmental data to cut down on energy use and material waste. Architects can generate and compare thousands of different versions of a design in minutes, making decisions based on hard data, not just a gut feeling. And crucially, these super precise digital models can talk directly to robots and 3D printers, which is what makes these complex forms actually buildable in the first place.
So where do you find inspiration for these incredibly optimized systems? Well, the best examples have been around for millions of years. It turns out nature is the original parametric designer.
And that's exactly what we're doing. We're learning from it. It's a field called biomimicry. Just look at the Al Bahar Towers in Abu Dhabi. They have this incredible facade with over 1,000 panels that open and close in response to the sun, just like a flower, to control the heat and light inside. It's a dynamic, responsive system inspired by nature and made possible by algorithms. This is all already so powerful, but honestly, it's just the beginning. If we can learn from adaptive systems in nature, it makes you wonder, how much more can we hand over to the machine? The future isn't just being designed, it's being generated.
The next massive leap is from parametric design to something called generative design.
And this is where the computer stops being just a really sophisticated tool and starts becoming more of a creative partner. So what's the big difference? With parametric design, the designer is still in the driver's seat, defining the rules and tweaking the parameters. But with generative design, the designer just sets the goals. They might say, I need a design that maximizes natural light, minimizes structural material, and stays under budget. Then, an AI explores all the possibilities and comes back with thousands of high-performing options, many of which a human would never have even imagined.
This shift is unlocking some truly incredible possibilities for the future. We're talking about a seamless, real-time connection between the design, the plans, and the actual construction. We're talking about robots and giant 3D printers building these complex structures directly from the data. We're even talking about using AI to predict how a building will perform and what it will need decades from now.
So ultimately, we're moving away from designing static objects and toward creating dynamic, intelligent systems, architecture that can respond, adapt, and even learn. And that leaves us with one final thought to chew on. If our buildings can learn and adapt, what else in our world should?